Well, we've actually kind of shut a door here, but I don't want you to do it in the sense that everything that's happened in the last, almost 4 weeks gets forgotten, because that's not a good idea. But we've opened a different chapter. We're opening a new door. And what we're looking at is the shortcut way. So every derivative that we calculate from now on is going to be done the fast shortcut way. No more limits as x tends to 0, or no more limits as x tends to a, right? We're going to do it using various shortcut rules. And starting at 3.1 and progressing for most of chapter 3, we're going to look at how to find the derivative, right? The function that tells you the slope of the tangent line at any given point, how to find that by using various formula and rules. And here's a list of some of the expressions you're going to do in the next 2 days. Quite a few overlaps, because we're going to do polynomials. We're going to do simple radicals, right? Square root of x, cube root of x squared, x to 2/3, right? Things like that. We're going to do simple rationals, 5 over x squared, 5 over x cubed, things like that. We're just going to do expressions. That's just my coverall for just expressions, things like x times x plus 1 squared, right? Just things like that. A new guy that we haven't talked about, how to differentiate e to the x. Remember the exponential function, e to the x. How to differentiate that. How to differentiate a little bit more complicated ones, and equations of tangent lines and equation of normal lines. And that's going to take us today and tomorrow. So there's 50 questions in this section. It's probably the biggest homework section you've ever got. But a lot of them, hopefully, should be reasonably quick. So let's jump right in and show you an example of a polynomial. Now, we've done plenty of these, so hopefully I won't spend too much time on this group. Don't we use a guy called the power rule for that? And according to that rule, if you want to find the derivative, we'll call it f dash of x, you take each term and you use the power rule on it. And the power rule essentially says multiply by the power and divide by the new power. Sorry, multiply, God, don't know where that came from. Multiply by the power and reduce the power by 1. So you get 21x squared. This guy here, multiply by the power and reduce it by 1. The last two terms, the linear terms, tend to have their own little special case. The 7x gets you 7, and doesn't the negative 11 just disappear? You don't get anything out of it. And we've already used that a lot. So is it okay if I don't do any more polynomials? Do you feel you know how to do those guys? Right, out of the way. So that's basically number 1 covered. Let's move on to number 2. We have done some of them, but I think we probably need a few more before we call it a day. This is one version of a radical. A radical can be written as a fractional power, right? You might also get a radical written like that. These two things are actually the same thing. If you do a little bit of algebra and you bring up stuff from Math 99, can you remember that fractional powers can be written as radicals, and radicals are actually just fractional powers, right? Now, these guys are also the chain rule, right? It works with these situations as well. You multiply by the power. So if I multiply them together, I get 8/3. And then you reduce the power by 1, and you get that. Now, what you typically don't need to do in polynomials, but you do need to do in many of these, is that you have to rewrite the thing, okay? So the style point rule, as I call it, so it looks like the original. Now, there's a bit of argument here, kind of in the math world, about this particular one. This is quite acceptable. and I would be fine with it. But some, I guess you would call them purists, would say that it should be written like that. Can you see how this becomes that? Aren't I using the fact that a negative power becomes a positive? Me personally, I'm on the, I think that is totally valid, because it really is, in my opinion, isn't this and this the same format? This and this is also the same format, but to me that's good. So leave it. Of course, you're going to change letters, so let's not think of everything called f of x. Let's do a g of x. And let's suppose that you get 8 square root of x. Now, in some questions, the radical is written in a form that's not useful for finding derivatives. So in this case, you have to convert it to a fractional power. In this situation, you can now use the power rule. Multiply by the power and then reduce it by 1. And this might seem like I'm disagreeing with my my rule here, but I'm not. In this question here, I said it's okay to leave the answer like this, and the reason why, because it looks like the original. This guy does not look like the original. Do you see it? It's quite different looking. So this one does need to be fixed, and everybody kind of in the math world agrees that this is not a good version of the final answer. So it kind of works in 2 stages. The first stage is to do that, and then the last stage is to do that. So that is the final answer. Are you okay with the algebra necessary to take radicals and convert them so you can differentiate? And then how to take the answer and convert them so that they look like the original? Because there's a fair amount of algebra here and very little calculus. In fact, the only part of what you're looking at that's calculus is the bit that goes from here to here. Isn't everything else just algebra of some kind or another? Right. Let's do another one of these guys. How about now in this case, the variable is v, and the notation I'm going to use is y dashed to represent the derivative. And it's really essentially made up of 2 guys. Power rule takes care of that guy. Oh, I guess I need an extra line here. But this fella has to be called 3/2. Right? The square root of v cubed is 3/2 as a power. Now, multiply together, you get -6 v to the half. And in this question, there's your finished product. Are we good so far? Radicals just are fractional powers. Turn them into whatever fractional power you need if you have to. Use the power rule and then make your answer look pretty by making it look like the original. And that depends on what the original looks like. If the original was fractional power, it's okay to have an answer as a fractional power. If the original has a square root, you better have a square root in the answer, right? Or a cube root, or whatever root happens to be going on at the time. Is that enough radicals, or do you want to see some more radicals? Feel good with radicals as well now? Power rule, same rule, cool. Losing track of my list. Oh, rationals. First guy in the world to look at a rational, wants to differentiate it. Any ideas what I'm going to do? to make that happen?
Would it be 10x to the negative third?
It would. Now, that's not the answer. I haven't differentiated it yet, but that's exactly what you have to do first. Agreed? Now, if it's written in that form, what rule do you think I'm now going to use to find its derivative?
The power rule.
I'm going to use the power rule. Hey, this is a pretty versatile rule, isn't it? You can use it for polynomials, right? X cubes and plus 4x squareds. You can use it for square root of x's and cube root of x squareds and things like that, radicals. And now it looks like you can even use it for simple fractions, things that have 10 over x cubed, 4 over x squared. So let's see what its derivative looks like. Multiply by the power and then reduce the power by 1. And no, it is not -2, it's -4. Remember subtracting, right? It's -4 when you reduce it by 1. Do you think that is the final answer, like they say in the quiz show? And if it's not the final answer, what will the final answer look like?
It doesn't look like the first one because it's a -4. It's not over anything, so it'd be -30 over x to the 4th.
And we are finished. Do you see my style point rule? Make it look like the original. Right. Now we do that so that everybody in like the universe gets the same answer, but they also get the same answer written in the same format. It just makes life easy, isn't it? If everybody writes the same answer the same way. Because if you allow people just to like stop where they feel like it, and don't you have to then look at your working and look at their working and say, okay, mine is the same as his, everything's fine. Whereas if you all finish at the same point, you just say, did you get that? Yep, we're good. Right. So try another one. G of U is a pretty ugly looking expression. First thing I'm going to have to do is to rewrite them as negative powers. So far, so good. Now I can do calculus and I'll use the power rule. Multiply by the power, reduce it by 1. 2 negatives make a plus, so you multiply by the power, reduce it by 1. Multiply by the power, reduce it by 1. And then I look at it and I say, does that look anything like these guys? And I'm looking and I'm saying, So style point says, this power rule is doing a lot of work, isn't it? It's doing some heavy lifting here. What it's essentially allowing us to do is to find, using a shortcut method, the power rule, lots and lots of different functions. Here's one for you to try. Find the derivative of that ugly expression. And by the way, this is number 4. expressions simple. So find that guy. While I give you. If you know what you're doing, you can do it in a minute. Go for it. Last few seconds. Okay, just shout it out. Starting at the left, and whoever feels comfortable enough to tell me the answer. What's the derivative?
I have 21x squared minus x to
Correct.
the negative 1/2 minus 6 over x. Right.
Minus x to negative 1/2. Okay.
Mhm.
Minus 6x.
Over
Anything else?
x cubed, sorry. The 6 is on top.
Oh, yeah.
Yeah, I prettied it up, sorry.
Yeah, you're right. I'm just writing this line down.
Right.
Is there anything here?
No.
Did I forget to write something down?
Oh, the x.
What about minus 4x?
X came down, so it's just 4. My bad.
Okay, agreed.
Yep.
So, but I think what you said. Well, let's do this guy. Wouldn't that be 1 over x to the half?
X. Mm-hmm.
And but that in its turn gets you that.
I didn't
Agreed?
pretty that one. Yeah.
So make it pretty. Keep everybody in the math world happy. So 21x squared minus 4, a negative 1 over square root of x, and a negative 6 over x cubed. Hopefully you all got those 4 pieces. Now, the thing about expressions, isn't it just using all these things, you know, using a bit of this version, some that looks a bit like this, and that. So all you're doing is putting things together. It's not that this expression, although it might look, and it probably does look pretty horrendous, it's really made up of simple little jobs. Just differentiate each piece according to the rule that you would use. Right? They're all going to be the general, but in different versions of that rule. So how about this fella? The exponential function. He is not the chain rule. I'm not even going to write down what you would get if you tried to use the chain rule on him, because if I did, it might stick in your head and you think it's right. This is not the chain rule. The derivative of the exponential function e to the x has nothing to do with the chain rule. It's a totally new rule. And it doesn't even get a name because it is so simple, I guess it wasn't worth a name. But it is magic, because I'm just going to tell you what the answer is, and you're going to say, okay, I'll trust you. The derivative of e to the x is e to the x. Would you agree it's probably not worth giving it a name? Right? Yeah, it don't really do that much to get its derivative.
Why is it just e to the x?
That is the good question. First rule is because I told you it is, but that's not a good reason. Because I could tell you lies. I'm not, by the way, it is e to the x. I'm not telling you lies, but I could be. So I'm going to prove it to you. Not because you need to prove it, but it might make you feel better if I prove it to you. Okay? So I'm going to call it f of x equal to e to the x. And I'm going to find the derivative using the limit as h tends to 0 of f of x plus h, take away f of x over h. You know that's the same as f dashed a, right? I've just replaced the x's with a's, right? That's all I've done there. Now that's going to be the limit as h tends to 0. Well, if the function's called e to the x, f of x plus h is just f of x plus h. Take away f of x over h. And this is going to be the limit as h tends to 0. And I am going to pull out a common factor of e to the x. And if I do that, this is what you've now got. Now, the only part that might be a bit troublesome to you is how is e to the x a common factor and why do you get this? So as a kind of side note, let me explain how that is allowed. E to the x plus h can be thought of as e to the x times e to the h. Don't you just add powers together? Great. So that is the same as that. So if I did e to the x plus h, take away e to the x, I could have written it as e to the x times e to the h, take away e to the x, and then I can pull out an e to the x as a common factor. So hopefully I've convinced you that that's allowed. So far, so good. Now, the troublesome part. See this thing here? E to the h, take away 1 all over h. See this guy here? He has a limit, and its limit is 1. So what you get is e to the x times 1. So the answer is e to the x. Now, proving that the limit to that is equal to 1 is very complicated, but it is true. But I can at least back it up. Couldn't you just pick a table of values like 0.01, 0.001, 0.50 zeros in a 1, and you would be able to estimate that answer. And if you did that, you'll agree that the answer is dead close to 1, so it probably is 1. So you don't need to know this. I'm never going to ask you a question to prove this. But for the people who don't like magic, have I pseudo at least made you feel a little bit better that it's e to the x? Right. Because I don't like magic if I can do it. Well, what does that mean? It means differentiating e to the x is not going to be the worst thing in the world to do. Right? Plus, there's not an awful lot you can do with e to the x. You get a 5 e to the x. Okay, well, if I do that, the answer is 5 e to the x. I guess you could have negative 2 e to the y. And so the derivative of that guy would be negative 2 e to the y. Do you know my favorite function to differentiate is e to the x? I don't think I've ever screwed up differentiating an e to the x. I've probably screwed up every other thing, even simple things like 5x cubed. For some reason, you multiply 5 times 3 and you get 12. You know, whatever weird thing your brain does. But would you agree you'd be really hard pushed to screw up that one? Right? I can't even think how you would manage to do it unless you really tried hard. I mean, if you stick a 1 there, isn't that the answer? I mean, nothing. It's the same as what you started. But can we chalk off number 5 then? So I'm assuming, is it okay to say we know how to differentiate e to the x's and what can you do to them? We've covered them. So let's look at complex expressions. Whoa, these guys, there isn't one version of these. This is just a catch-all for weird stuff, right? So complex expressions are weird stuff. You'll know when you see them, when you see a weird thing, right? So here is h of z. And it is z to the power of 1.2 plus 2z to the power of 1.5. Would you agree that is a weird expression? It's not that often you'll see a power that is a decimal, right? But the power rule still works. You multiply by the power, and then you reduce the power by 1. You multiply by the power, and then you reduce the power by 1. And would you agree that that one is finished because it looks just like the original? It looks equally weird. How about this weird one? I need to differentiate this. And it's a pretty ugly, weird expression, right? And I can't just ignore the problem. And I have to figure a way that gets me the right answer. But the way it's written right now isn't helping. Is there anything algebraically you could do to that that could get it into a form that I can use the power rule on? I want to take this expression and rewrite it.
Can you multiply by t on the denominator to the
almost?
numerator? Yeah.
Yes. If what you've said is what I think you've said, I'm going to say yes. So I'm going to write it down and you say yes, that's what I meant, right? Okay. There are two ways to look at this, both work. You can multiply everybody by t to the -1. And if you do that, you get 3t minus 5 plus t to the -1. So this expression turns into that. What's the advantage? Do you notice that this guy, you can do the power rule on? This guy, you couldn't. So you were doing nodes there. Was that what you were getting at, Kelsey? Right. Okay. So you differentiate now. 3t just gets you 3. The -5 gets you nothing, right? You don't write anything down. And this guy here is you multiply by the power, and then you reduce the power by 1. And now we have to think about style points. Would you agree that the original version was a fraction? Right. So I'm going to make at least an attempt to have a fraction-like answer.
For the 3t,
and I will let that one go.
For the 3t squared,
Yes.
why does it turn into 3t? Why doesn't it turn into 6t?
Oh, shooting space. Did you all catch that deliberate mistake? I just wrote it down wrong.
Okay.
Oh, wait a minute. No.
No.
Oh, I'm right. 3t squared times t to the -1 is 3t.
Okay. Yes.
So this is algebra and this is calculus, right? I haven't done anything except algebra here. And getting from here to here, I've done calculus. Okay. Now, I said there's two ways to approach this question. That way is probably the way I might have went. Half the time I probably would. Let me show you a different approach to the same question. And for some people, not everyone, this new algebra approach kind of makes more sense to them. Were any of you thinking that maybe you could just split it into 3 fractions? And then if you simplify each fraction, and this fellow you turn into a negative power, do you see you get to the same place? A lot of the algebra that you use, let me phrase this, not everybody's brain works the same way, and some ways of doing things are more intuitive to them. I understand that way. It makes sense to me. And when something makes sense to you, you typically tend to do it correct more times than you don't. And if something is just a weird rule that you don't really think makes sense, but you know it works because it works, you're less comfortable with that method and you sometimes make more mistakes because of that. So I'm just saying, like, there's 2 ways to do this. Me personally, my brain goes one way, your brain might go the other way. It ain't any, this is the only right way to do it, right? There's 2 correct ways to do this. Who knows, you might come up with a third algebraic way. I can't think of one, but you might. And if that way makes sense to you, as long as when you're finished, before you differentiate, you get the guy that looks like that, right? If you get to here, then it must be a pretty, it's a valid method. Cool. How about?
You forgot to add a little, I don't know what you call it, the little dash above the F on that one. At the...
I did, and I just forgot to do something else to this one, but I did it in the last one, so I should do it. Shouldn't we do style points? I did it to the other one as well. But yeah, I forgot that. That is true. How about this fella?
Professor.
Yes.
In the last expression too, the 5 drops out because it no longer has a t for the final, yeah.
Did I do that? Oh, and so does the t
Shouldn't
drop
the
out.
final t be squared?
We are. There is the right answer. Yes, it should be. That's the right answer. Ignore everything that went on before. God, it doesn't take much to get my brain back to front. Okay, here is a different complex expression. I really think there's only probably one way to tackle this question. Would you agree that I have to do some algebra before I can use the power rule? And would you also agree that the algebra is just foiling? So I don't think there's many decisions here. I'll try and make sure I foil it correctly. I get a w cubed. I get a w. I get a w squared. Whoops. And finally, I get a +1. And to get its derivative, then power rule. And this drives my wife crazy. I know that's the right answer, and I know that's the same thing, but I still have to write that. And it's nitpicky, and nobody in their right mind would ever take a point off you in a test, and I won't either. But I have to do it that way, because it just drives me crazy to see a polynomial not written in order of its powers. I mean, it's nitpicky, totally nitpicky. I have many idiosyncrasies, as you probably know. Here's one of them. I do not like pictures that are an angle on the wall. Right? Don't like it. drives me crazy, you know. I'm a picture straightener. Right? If I see something on the wall, picture should be parallel, right? The bottom should be straight. If you were going to go into someone's house and I see a picture and I know it's like 5 degrees off, do you know how annoying it is to my brain? I want to go over and fix it, but I'm not allowed to, because you're not allowed to touch other people's pictures, right? That's a social rule. Is that a social rule, Teresa? You're not allowed to straighten other people's pictures, even although they drive you crazy because it. Come on, how hard is it to straighten a picture? Right,
My
whatever.
husband does that too.
Dodge.
So
Are you a
sometimes
picture straightener, Teresa?
Not really. I mean, I am, but my husband is extreme. So sometimes me and the kids we'll just go around the house and we'll move little things, and then it drives him nuts, and he fixes it all.
Oh,
That's cruel. That's like cruel and unusual punishment, man.
exactly. That's a divorce case. I can see that coming up. And what did she do? She went round the house and she moved the pictures to annoy me.
What? It sounds
And
like
she
she's
got the
giving him
kids.
something to do.
Yeah, and she got the kids to take part. Yeah, okay. Oh God, but wouldn't the world be a boring place if we were all the same, right? The world needs some picture straighteners, right? And they also need some picture unstraighteners, don't we? There's probably people in the world who don't like things to be straight. They like them all to be a little bit crooked, right? A little bit more natural. And I've drifted. Oh, before we go, we've done a big chunk of stuff here, which is great. So it'll mean tomorrow we'll get through a lot more, probably, because we've done 90% of what we need to know, but there are a few others. I want to show you some really weird stuff. You know that you can differentiate formulas. Now, just think of that guy as y, and think of that guy as x. Isn't a equal pi r squared a little bit like y equals pi x squared, right? You can differentiate it. Now, if you differentiate the area formula, I'll call it a dashed, isn't a power rule. Great. And what's the power rule? Well, you multiply by the power and you reduce it by 1. Have you ever seen the formula 2 pi r? Isn't it the circumference of a circle? That is not a coincidence. If you think of the rate of change as being one way of thinking about a derivative, the rate of change of the area of a circle, which is how big it gets, isn't it really, it gets big according to adding a circumference? Isn't it? Like visually, imagine a circle and then you added a little bit more to it. Isn't the bit that you're adding really just a circumference worth? You might not know this formula, I hope you do. And do you know that's the formula for the volume of a sphere? If you differentiate that formula, you multiply by the power and then you reduce the power by 1, you get that. Do you know that's the formula for the surface area of a sphere? So if you've got time and interest, take some of the formulas that you got in physics or chemistry and differentiate them according to whatever the other variable is. And there's a very, very good chance that you're looking at another chemistry or physics formula. You're looking at the rate of change formula of whatever the original was. Does anybody know this formula? What is it? Anybody remember that guy? It's the formula that tells you the distance traveled by an object whose initial speed is u and whose acceleration is a. If you differentiate that formula, you get u plus at, which is the formula that tells you the velocity of that same object after t units of time. So take any chemistry formula that you've got, or physics formula, or electronics formula, or anybody's formula, differentiate it according to the variable. In this case, the variable is t. And there's a very good chance that that new formula is also something that you know. When I was first told that, it helped me because I have an atrocious memory. I really do. I can't remember names and places and all sorts of things. But God gave me one thing that it was nice of him to do. And he gave me, math comes easy to me and I visualize things. So when I was in a physics class and I had to remember all these different formulas, and it was kind of like learning a language, right? Just remember this formula, right? We weren't allowed to write them down and keep them. You had to do them from scratch. I would just remember one of them and differentiate everybody to get the other ones. So I didn't need to remember 10 formulas. I only needed to remember 3 or 4. And then I knew the math, I could get the others. And you do high level math, you find that everything's connected to everything through calculus anyway. So if you know calculus, you can do it. I used it to do trig identities as well. You know how many trig identities there are in the world? You know, if you start with a trig identity and you differentiate it, you get another trig identity. So I can use, I only need to remember one of them and then I can get all sorts of other ones from that, which was kind of just the way my brain works. Okay, we have learned some really cool stuff today. And I told some really good jokes today, regardless of what Kelsey thinks. So have a nice day, everybody. Say hi and bye-bye.